Hi everybody, my name is Rob, and today we're going to be load testing a small Kubernetes cluster. We're going to subject it to a sudden load spike to see how it reacts. Now, in this video, we're going to be going over the tech stack as well as the actual experiment itself. And I would encourage everybody to check out the actual code involved in each of these repos. We have a code for the infrastructure as code, as well as the API itself. All of it's available at my GitHub page. So I'd encourage you to go take a look. Links are all in the bottom. Cool. So the tech stack itself is largely the API, which is running a Go service, very straightforward CRUD API. We created a few endpoints, a /users endpoint and a /compute endpoint. The deployment itself is using GitOps, powered by Argo CD and GitHub Actions. The monitoring stack is the Prometheus Grafana stack that we'll be watching the cluster with. And the actual infrastructure itself is largely AWS and MongoDB for the data store. And we're actually going to be load testing the cluster itself using K6, which is kind of under the Grafana Prometheus family. The architecture is probably no surprise. It's a pretty standard architecture. We have a CloudFront that fronts the whole architecture. We are using Route 53 for DNS. We have a two-tier VPC with public subnets and private, and our EKS cluster is in the private subnet, and the requests are forwarded into that Kubernetes cluster through a network load balancer. We egress our traffic to the database and other sources through a NAT gateway. So the first experiment that we're going to do is the sudden load on the cluster. So this could happen for a bunch of reasons in real life. It could be a new customer being onboarded. It could be a response to a real world event. It could be a malicious attack on your cluster. And so what we're trying to do is simulate what actually happens in this scenario and what we can do to prevent any sort of bad outcomes as a result of something like this. So in this experiment, we're going to be hitting the /compute endpoint of our Go API. This is a very simple function that is designed to simulate CPU load. So it's just a straightforward calculation and then a sleep. This is going to help us simulate kind of like a CPU intensive load that we might have on some of our more complex endpoints. Cool. So before we get into that, I think there's a few things that we want to look at. The first one being how our cluster is set up right now. So if I go on over to our code and I look in the infra directory of our K8s API, I'll go into our values YAML, which is defining all of the values that update our Kubernetes objects. We'll see we have a single replica when we load up. So it's just a single API pod. Wouldn't need any more for a simple API like ours. And we have some auto scaling here, which is settings of our Horizontal Pod Autoscaler, which if you go into templates, you can see it configured here. And so we have auto scaling enabled with a min replica of 1 and a max replica of 10. And we're going to scale based on target CPU utilization percentage, so 50%. So when the CPU utilization on average reaches 50%, the HPA will kick in and we'll scale the cluster. The other thing I wanted to show was the load tests themselves. And so here is the load spike configuration that we're going to be running in K6. It's a very simple script. This is all it is. It's going to ramp up with a target of 1 virtual CPU, and then it's going to hit a peak of 10, and then it's going to ramp down, and then it's going to finish. And so this test itself will take about 9 minutes, and our threshold here is our P95 less than 500 milliseconds. You can see we're just hitting the compute endpoint, and we send a cache control header because we actually don't want our CloudFront doing any caching. So before we actually start the experiment, we are going to switch over to our AWS console, and we're going to very quickly update our CloudFront distribution. what we want to do is adjust the TTL. So if you scroll down here, this is like the default. So our maximum TTL is going to be 1 second, and our default is going to be 0. So we're going to save these changes. So what this is doing is basically going to prevent our CloudFront from actually caching anything, so that every request that we send to the API, it's going to see. And if we go over to our webpage, just API at anytime agile, the main endpoint, I'm healthy. We have a /users endpoint, which has a bunch of users that get loaded in. If I hit the /compute endpoint, which is like the burn endpoint that we're going to be using for this experiment, you'll see it loads right away. But if you hit it multiple times, you'll see that the page actually does take a bit of time to load. Cool. So this is our experiment view, and on the top right corner, we have the Kubernetes cluster view, which is focused on the API namespace, and we currently have a single API pod running in the API namespace under no load at all, because we haven't started the test yet. On the left side, we have a view of all of the hits to the various endpoints of the API. So for this experiment, we're going to be hitting the /compute endpoint. So we're going to see that endpoint, which is in blue here, spike up. On the bottom left, we have the Horizontal Pod Autoscaler view. And so this is going to give us insight into the scaling activities during the load test. And on the bottom right side, we have our load test interface. And so we're going to start the load test and observe the experiment. We're going to start to see the load come online. We can see the CPU is spiking pretty quickly, and the HPA kicks in and immediately scales out our cluster. Now, this is sped up, so there's a lot that's happened very quickly, but we'll notice that as the load spikes, the CPU utilization increases past 100%. We can also see that Grafana is having trouble loading, as indicated by the refreshing taking a bit of time. Awesome, test complete. So what happened? So we hit the cluster about 3,200 times, and the cluster performed. It served 100% of those requests successfully. We did get about 25 milliseconds of latency that we can observe kind of in the P95 there. But we did see the cluster struggling a bit. You would notice that Grafana, the UI, had trouble auto-updating at times, and so we did stress the cluster. And even further load of that nature would result in failed requests and impact your customer. So what can you do about it? CDNs and cluster right sizing. So if we hadn't disabled our CloudFront, we wouldn't have seen any of that load. Because it's originating from the same origin, it would have just served the cached version, and it would never have hit our API. So we wouldn't even have seen the spike. And so utilizing a CDN is the #1 way to avoid something like this. Additionally, we could have added more replicas. In this case, because we were hammering it, it wouldn't have had a huge effect, but it would have obviously taken load off of individual pods and distributed them across the fleet. And so adjusting max replicas is also an option here. With that being said, that wraps up the video. If you have any questions or comments, please do let me know. If you're interested in how this environment was set up, I have a video about that on my YouTube channel that you can check out and follow along yourself. But with that being said, thank you. I appreciate your time, and my name's Rob. I hope you enjoyed.